Welcome everyone. I'm Kristen Eulenbrock with the U.S. CIRES Project Office, and I want to thank you for joining us for today's webinar. I would like to give a few logistics to get us started. Today's webinar is going to last for about 1 hour. Each speaker is going to have about 10 to 12 minutes for their presentation, and after each speaker's presentation, we'll take a little bit of time for a couple of questions. To ask your questions, you have two ways to do that. You can raise your hand and I will take you off mute, or you can type your question into the chat feature as well, and then I will read that aloud for the speakers. I'm recording today's webinar, and I'll make that available on our YouTube channel a little later this week. Today's webinar is part of our Variation series of webinars, which is based on our quarterly publication that we just released somewhat recently here. The most recent edition is on the expansion of the tropics. This was co-edited by our guest editors, Kevin Grice from the University of Virginia and Paul Staton from Indiana University. Both Kevin and Paul are the co-chairs for our working group on this similar topic. So with that, I would like to welcome and introduce Kevin, who will do introductions for today.
All right, well, thanks, Kristen. So as Kristen mentioned, this issue of variations is related to the current U.S. CIRES working group on the changing width of the tropical belt that I'm a co-chair with, along with Paul Staton from Indiana. And so our group was formed in 2016 to basically target the subject of tropical expansion. And if you're not familiar with the issue of tropical expansion, it's basically the idea that the Hadley circulation, which governs sort of the wet regions near the equator and the dry regions in the subtropics, that this has been changing in the last several decades. And in particular, there's some concern that the poleward edge of the Hadley circulation and the associated subtropical dry zones might be moving poleward. And so there's been a lot of confusion and different conclusions in the literature on this, and that's kind of the point of our working group, is to kind of sort through these issues. And so there's sort of three targeted issues that we as a working group are investigating. The first is metrics, so how do we measure whether the tropics are expanding? The second is sort of what is the cause of their expansion? Is it natural cycles or is it anthropogenic forcing? And then lastly, what does this mean in terms of regional impacts? So this issue has 5 articles in it, and we're going to hear from 3 of the authors today. The first section of the working group, the metrics, has 1 article, and so Nick Davis is going to talk about that. The second section is about the variability, the attribution, forcing versus natural variability, and so we have 2 articles in the issue on that. The first is by Bob Allen on issues associated with the El Nino Southern Oscillation and the Pacific Decadal Oscillation, and unfortunately Bob cannot join us today. The second article on variability is by Isla Simpson from NCAR, and so you'll hear from her a little bit later. And then the final section of the issue is 2 articles on these impacts. The first is on impacts on land, and we'll hear from Jack Scheff from UNC Charlotte about those issues, and then from Carrie Cook from University of Texas wrote a nice article on ocean impacts, and unfortunately Carrie can also not join us today. So we'll hear one presentation on each of these issues, one on metrics, one on this variability, and one on sort of the regional impacts. And so with that, I'll turn it over to the first speaker, who's Nick Davis from CIRES and NOAA ESRL. He'll be talking about new insights into tropical belt metrics.
Great, thanks. So these are the other co-authors on the Variations newsletter on metrics. And before getting started with the details of the metrics, I think it's just worth, again, extending Kevin's discussion of what exactly do we mean by the tropical belt. So what I'm showing here is data from the Merituri analysis. And the shading here, where it's green, it shows relatively rainy regions, and where it's brown shows relatively dry regions. And the surface winds here are indicated by the vectors on the bottom plot, and the zonal mean vertical and meridional winds with the vertical component emphasized are shown here in this upper panel. And so in the zonal mean, you see the canonical Hadley circulation with rising motion at the equator and sinking motion in the subtropics at around 20 and 30 degrees latitude. And the sinking motion occurs preferentially on the eastern side of ocean basins, among other places, where the sinking motion tends to suppress precipitation. And the surface flow actually removes what little moisture is left here and converges it into the tropics in the intertropical convergence zone, where it goes on to fuel the circulation. And so this boundary here between the dry subtropics and the relatively rainy mid-latitudes is the climatic zone of interest. So if we want to understand how the future of Earth's surface climate is going to evolve, it's important to understand how the Hadley circulation edges may change. And in practice, this is actually quite difficult to do because we can't really measure the Hadley circulation directly from observation. And so historically, people have come up with a lot of different metrics to study Hadley cell expansion and the expansion of the tropical belt. And all of these fields here have been used to characterize the tropical belt edge latitude. And I'm going to focus in particular on a few metrics and a few fields in this discussion. So on the top, I'm showing outgoing long-wave radiation, which has this peak in the subtropics where the relatively dry surface and atmosphere is able to cool effectively to space. In the shading here is the mean meridional stream function, which is the standard way of looking at the Hadley cells. So the flow in the meridional and vertical plane here is parallel to the contours. And so these warm colors indicate clockwise rotation in this plane. And so, of course, we're interested in understanding variations in the edge latitudes of the Hadley cells, or the boundary between the Hadley cells and the Ferrel cells in both hemispheres. But again, we can't really get that directly from observations. And so folks in the past have used things like the zonal mean zonal wind, so here in these black contours, and they've measured things like the latitude of the subtropical jets. They've also, for example, looked at the structure of the tropopause, here shown in magenta, and identified the tropical belt edges as the latitude of the tropopause break, where it slopes abruptly from the tropics to the extratropics. People have also looked at where the zonal mean zonal wind is zero at the surface, which is also co-located with all these other metrics. The zero line is this dotted line here. And then now, more at the surface, people have also looked at things like the subtropical ridges and sea level pressure, here shown in blue, where the sinking motion is at the edge of the circulation. And then people have also looked at things like precipitation minus evaporation, which you can see is relatively negative in the subtropics, indicating that evaporation outpaces precipitation. And for the purposes of this presentation, I'm again going to focus on these sorts of metrics of the dynamics, things like the Hadley cell edges and the jet and the tropopause and the surface winds. But I'll briefly comment on the other metrics later. And for all these following plots, they're adapted from a recent paper produced by the working group. And so a key question here is, which metrics of these are related to one another, sort of in general, but also to the Hadley cell edges. Just because the metrics are climatologically located at a similar latitude doesn't mean they're necessarily representing the same physical structures and modes of variability. It'd also be good to understand which metrics can be related to observable quantities so we can develop a more robust estimate of past expansion. And then, of course, a related question is how these metrics project onto surface climate. And given this first question, the really important question, I think the answer is, why are the metrics related or not? And two early studies that were authored separately by members of this working group, and in particular the metrics subgroup, came out in the early stages of this working group. And they addressed this problem from different angles, using different models and timescales. And so the working group felt it was best to essentially come at this more systematically. And so the working group published a paper that revisits this relationship among metrics of tropical expansion. It's now WAD al. 2018. It was just accepted at Journal of Climate, and I think it'll be an early online release soon. And in this paper, we looked at 23 climate models from the Coupled Model Intercomparison Project Phase 5 using the pre-industrial control and abrupt 4x CO2 simulations. And the rationale for using models was that they have internally consistent dynamics and a large sample size, both in terms of the length of time we could look at and also in terms of the fact that we have 23 ensemble members. And the study looks at 9 metrics of the tropical belt edges. Here I'm focusing on the 5 that are really measuring the basic dynamics of the circulation. So this paper does examine things like precipitation minus evaporation and OLR, and again, I'll comment on that at the end. So kind of the most naive, but I think really useful way to see how the metrics relate to one another is to look at how their time series are correlated interannually. So this is showing you the correlations between annual mean tropical belt edge latitudes measured by each of these 5 metrics in the northern hemisphere and in the southern hemisphere. And the way to read this plot is to find your pair of metrics, say the subtropical jet and subtropical ridge, and you can find their correlation in the northern hemisphere here and then in the southern hemisphere here. And these upper numbers indicate the multi-model mean correlation coefficient. The parentheses indicate the standard deviation, and a star indicates the cases where a large majority of the models indicate a significant correlation. And if you even just use the color here as a guide, there's really 2 sets of metrics that pop out. On the one hand, you've got metrics like the latitude of 0 surface zonal wind, the latitude of the subtropical ridge, and the Hadley cell edge latitudes that tend to be well correlated robustly in both hemispheres in the models. And then on the other hand, you see correlations between the tropopause break and subtropical jet latitude in both hemispheres that are fairly robust and strong across the models. And there are either very minimal or non-existent correlations between these groups of metrics. So what this is telling us is that things like the tropopause break latitudes and the subtropical jet latitudes are essentially measuring a very different thing than the Hadley cell edge latitudes, the subtropical ridge, and the latitude of 0 surface zonal wind. And that's a bit interesting because there's good physical reasons why you might expect all of these metrics to tend to be related. So to take a stab at answering a little bit of the why these metrics are or are not related and just check if the metrics are actually doing what they think they're supposed to do, we regressed the different fields that the metrics are constructed from onto these annual mean tropical belt edge indices in the southern hemisphere. So we regressed things like the jet level wind shear, which is used to find the subtropical jet latitude onto the Hadley cell edge, the tropopause pressure onto the Hadley cell edge, and sea level pressure onto the Hadley cell edge. And then we also looked at the regression of tropopause pressure onto the subtropical jet latitude. And this is in the southern hemisphere, so left is poleward and right is equatorward. And the solid lines show what this field looks like when the Hadley cell edge is relatively poleward, and dashed is what the field looks like when the Hadley cell edge is relatively equatorward. And so for the jet level wind shear, which is basically just the upper level westerlies minus the surface winds, what you can see is that when the Hadley cell edge tends to be poleward, the jet level winds and the wind shear tend to be weaker everywhere in the tropics and subtropics. And this seems to go with how we understand things like temperature gradients relate to variations in the Hadley cell edges. So, for example, in general, when the Hadley cell is wider, temperature gradients are weaker. And so through thermal wind shear, you would expect the winds to be weaker. So variations in the Hadley cell edge do project onto upper level winds, but they don't actually move the actual maximum of the wind speeds, which is why there isn't really a relationship between the subtropical jet latitude and the Hadley cell edge. And it's the same sort of story with tropopause pressure. So when the Hadley cell is relatively poleward, the tropical tropopause pressure is a little higher, or the tropopause is lower, and vice versa in the extratropics. But you don't see a projection onto a shift in the latitude of the break, where this large gradient is between the tropics and the extratropics. Now, these vertical dashed lines are showing how the metrics shift. And of course, as we've seen, these metrics don't relate to the Hadley cell edges. But if you take the tropopause field and regress it onto the latitude of the subtropical jet, you find that when the subtropical jet tends to be poleward, the tropopause field actually shifts poleward. And of course, the metric here picks up on the shift of the tropopause break. Similarly, in the southern hemisphere, we find that as the Hadley cell edge shifts poleward, the subtropical ridge shifts poleward. And so just to summarize some of these basic results, the latitudes of the subtropical ridges, the zero surface zonal wind, are correlated with the Hadley cell edges, whereas on the other hand, the latitudes of the tropopause breaks are correlated with the latitudes of the subtropical jet, with really minimal cross correlations between these groups. And this corroborates some of the general conclusions of these two previous studies, but again in a more systematic and robust way. And as far as we can tell, the projection of these indices onto basic fields supports these conclusions. So what does this imply? That it means basically that the subtropical jet and tropopause break latitudes are not good proxies for the Hadley cell edge. I think it goes without saying that further work is needed to understand why, in terms of the dynamics, why we don't see that borne out. The good news is that a lot of these metrics that are correlated to the Hadley cell edges, like surface zonal wind and sea level pressure, are observable fields. So at least now we have some sort of observational proxies in a way to get it past Hadley cell edge latitude behavior, with some caveats that are detailed in this paper. And for a discussion of trends and the other metrics and seasonal variability, I'll point you to the paper, but just note that these relationships between metrics tend to carry over to the trends. And because of their complicated response to radiative forcings, it's difficult to use P-E and OLR to examine these sort of trends in the Hadley cell edges, but they are nevertheless impacted by variability in the Hadley cell. So thank you.
Great. Thanks, Nick, for the very nice presentation. We'll pause here just for a few minutes to see if we've got some questions. I'll remind folks you can raise your hand. There's a little button there on your participant screen to raise your hand, or you can type them into the chat feature. Okay, if there's no questions, then we'll move on to our next presenter. Nick will be around later, so we'll take some time for Q&A at the end as well if anything else arises. So we'll get started here with Isla. Let me take you off mute. Isla, you with us?
Yep.
Great,
Can you hear me?
thank you. Yes, please go ahead.
Okay, thanks. So I'm going to talk about natural variability in the width of the tropics, and so this is work that's come out of the various discussions in the US CIRES working group. So in many aspects of climate change, people have demonstrated the role that natural variability can play over our historical record and the role that it can play in projected future trends if you just have an individual realization with a model. And so expansion of the tropics isn't an exception to this. A number of studies have demonstrated the influence that natural variability can play on what we observe in terms of tropical expansion. And so here I'm just going to kind of follow pretty similar procedures to what have been used by these previous authors to illustrate the influence that natural variability can have on trends over the typical length that we use in our observational record. And then I'll also try and say something about what the nature of this natural variability is. So as Nick just discussed, there are a number of different metrics that can be used to describe the width of the tropics. And I'm here just going to illustrate natural variability using one of them. And so that's going to be the latitude of transition of zonal mean, zonal wind from easterlies to westerlies. And so this is a metric that's strongly correlated with the zonal mean stream function, but is pretty well more constrained in reanalyses. So I'm going to focus on annual mean tropical width, so the difference between the northern hemisphere and the southern hemisphere edge. So this is a time series of annual mean tropical width, and so roughly a decade ago it was realized that since our observational records began, there's been kind of a general tendency towards a widening of the tropics, which you can kind of see through these time series. But if you take a linear trend over this time series in these three different reanalyses, you see that they don't really agree. ERA Interim and JRA 55 have a trend of roughly 0.3 or 0.35 degrees latitude per decade over this period, whereas MERA 2 has a considerably weaker trend. So I'm not entirely sure which of these are more correct, but in any case, at most we're probably talking about an observed trend of about 0.35 degrees latitude per decade since records began, well, satellite records began in 1979 or so. So an important question to address then is what role could natural variability have played in these trends over our historical record? And so that's pretty difficult to assess directly in the observations. We can't really go back past 1979 or so to look at this. The reanalyses don't really agree. at least in the long-term trends as well. But we can look in models. So here I'm showing in the bottom panel is a time series of tropical width for the 40 members of the CESM Large Ensemble. So these are historical simulations that have been run under CMIP 5 forcings. Each member started from the same ocean and sea ice states in 1920, and then some additional round-off level perturbation was added to introduce noise and therefore a different evolution of internal variability. So the black line is the ensemble mean, so you can think of that to a good approximation, any trends in this to be due to external forcings. And so you can see there's a slight widening trend in the ensemble mean. But then on top of that, obviously, the gray lines are all over the place because of internal variability. So we can compare the trends that we've observed over our historical record with the various trends that occur in these different members of the large ensemble. So here I'm showing in the gray points the trend in annual mean tropical width for each of the 40 members of the large ensemble, and then the black point is the ensemble mean, and so you can think of that to a good approximation as being the externally forced trend. So the ensemble mean suggests there's been a forced trend of around 0.13 degrees latitude per decade. But then if you combine that forced trend with internal variability, you can get any trends ranging between a minimum here of minus 0.04 degrees latitude per decade, and then a maximum here of 0.43 degrees latitude per decade due to internal variability. And so these encompass the observations. So we may question, does the model accurately simulate internal variability? And it's pretty difficult to assess that on low frequencies, but we can at least assess whether on high frequencies it simulates reasonable variability. So on the right panel here, I'm showing the interannual standard deviation of tropical width for the reanalyses in the colored points, and then the large ensemble with CESM in the gray points. And so you see that the model points encompass the reanalyses. So we don't have any indication here that the variability in the model is deficient, at least on the high frequencies. So then we can try and assess, is the trend that we've actually observed over the observational record greater than what we could expect to have arisen from natural variability alone? And so to do that, we can compare the trends with trends that we see in long pre-industrial control simulations. So these are model simulations in which there's no external forcing, and so any trends that arise would have to be due to internal variability. And so here I'm illustrating two trends within this pre-industrial control simulation in red that are just arising from internal variability. So I'm going to compare the observed trend with the range of trends that we can see in these pre-industrial control simulations, both with CESM and then with other CMIP 5 models as well. So here we've got our observed trends in the colored points, and then the black lines are showing the 2.5th to 97.5th percentile range of trends that you can obtain in these pre-industrial control simulations. So what this tells us is that internal variability is capable of producing trends, depending on which model you're looking at, but trends roughly between about minus 0.25 and plus 2.5 degrees latitude per decade. And then it depends on which reanalysis you're looking at, but for ERA interim and JRA, the trends that have been observed over this 38-year record lie on the edge of the distribution of what you could get from internal variability or outside of it. So this is suggesting that the trends that we've seen over the last 38 years very likely need external forcings to be able to explain them, and that's consistent with the fact that the large ensemble shows an externally forced widening of about 0.13 degrees latitude per decade. So at least determined by these reanalyses, we probably need external forcings to explain what's been seen. This is only true really of the annual mean tropical width. If you look at different hemispheres individually, or if you look at individual seasons, the variability is sufficiently large that any trends that have been observed are actually not outside of what you can obtain with internal variability alone. So then, just want to finish up by saying something about what the nature of this variability is, and trying to address, is it more than just simply sampling year-to-year variability? Do we need some longer timescale modes in the ocean, for example, to explain the trends that arise through internal variability alone? So to try and assess this, we can compare. Well, first of all, we can take the long pre-industrial control simulation, which contains low frequency modes of variability associated with atmosphere-ocean coupling. Then we can just randomly sample individual years completely at random and string them together to make a new time series and assess what kind of trends can we get in this constructed time series, which by construction no longer contains those low frequency modes and the autocorrelation associated with them. So I'm going to go back to this plot here, and then I'm going to add on some circles which are going to show the 2.5th to 97.5th percentile range of trends from these constructed time series, which have just been obtained by randomly sampling individual years. So these trends will basically be due to sampling of interannual variability. And so you see that these circles are at a pretty similar place as the 2.5th to 97.5th percentile range of the original control runs. And so this suggests that you can get a large portion of these trends, so anything between minus 0.25 and plus 2.5 degrees per latitude per decade, just from the sampling of year-to-year variability. We don't need to invoke low-frequency modes of variability to explain them. That being said, as Kevin mentioned at the beginning, there are pretty strong indications that ENSO or the PDO is linked to variability in the width of the tropics, although that previous analysis suggested that maybe it's just the sampling of individual ENSO events. We don't need to invoke a low-frequency mode like the PDO. So I'm just going to finish up by trying to assess what's the relative role of sea surface temperature variability and internal atmospheric variability on the kind of trends that we see on the width of the tropics. So for this, I'm just going to compare the same long pre-industrial control simulation with CESM with an equivalent simulation just with the atmosphere only with prescribed climatological sea surface temperatures that have been taken from the pre-industrial control run. So the first simulation has sea surface temperature variability, and the second one does not. So the left panel here is showing the interannual standard deviation in the width of the tropics in the fully coupled simulation with sea surface temperature variability. And then the right is the range of trends you can obtain over a 38-year record. So again, anything between about minus 0.25 and plus 0.25 or so. Now, this point is showing what you get in the climatological sea surface temperature run. So the variability here has to be due to just internal atmospheric processes. So we have roughly 70% of the standard deviation that is seen in the coupled simulation. And then when you look at the range of trends, you can still obtain anything between trends of around about 0.2 degrees latitude per decade just from atmospheric internal variability alone. So clearly, SST variability is an important component, but atmospheric internal variability is quite a dominant component, and you can get pretty large trends over a 38-year record just due to that. We can go one step further and try and say what aspects of SST variability is most important. And so here I'm showing what you get if you take the coupled run and you regress out the contribution that's related to ENSO through the Nino 3.4 index. And so once you remove that component, you end up roughly with a similar interannual standard deviation to what's seen in the climatological sea surface temperature run, and you end up with a similar order of magnitude trends. And so this is suggesting that the SST influence is primarily occurring through ENSO. So to summarize, natural internal variability can give rise to trends in the width of the tropics over a 38-year record of roughly 0.25 degrees latitude per decade, as indicated by the model. So this is assuming that the model's variability is realistic, but given that I think much of this is just sampling of interannual variability, and we can see that the interannual variability is realistic in the models, this is probably true of the real world as well. These trends that arise are, as I said, primarily due to the random sampling of year-to-year fluctuations, and it's a combination of internal atmospheric variability and also an important contribution from ENSO. So internal atmospheric variability alone can give rise to trends of about 0.2 degrees latitude per decade over a 38-year record. And so the historical trends that we have seen, at least suggested by some of the reanalyses, are unlikely to have arisen from internal variability alone, which is consistent with the fact that the large ensemble suggests a forced trend of about 0.1 degrees latitude per decade. But if we were to just look at individual hemispheres or individual seasons, which I've not shown here, but it's in the variations article, the trends that have been observed in that case are not outside of what could arise from natural variability alone. So thank you.
Great, thanks, Isla. I will pause here again for any questions for her. Okay, let's move on to our final speaker. Thank you very much, Isla, for your presentation. And our last speaker in today's webinar is going to be Jack. Jack, are you with us? Please go ahead. And you may be on mute. Yeah, there we go.
There I am. Yeah, I had to unmute myself there. Hello, everyone. So I might be coming from a little bit of a different perspective here, since I wasn't part of the CIRES working group, and actually really haven't worked on Hadley cell edge latitude or tropical belt width, strictly defined at all. But I think I was probably asked to write the article just because I've done some earlier work looking at actual sort of projected trends in precipitation in subtropical regions, and sort of thought about how those might be related or not related to tropical expansion. But the connection to tropical expansion here is going to be pretty qualitative. I'm going to be showing you a lot of maps, and I'm going to be showing you where it seems from looking at the map that this subtropical expansion phenomenon, at least in future CMIP runs, causes land drying, and where it doesn't. And I'm going to be trying to make the point that actually it's really just certain places on land that, at least according to the models, that we need to be concerned about in terms of hydrological impacts from this. So let me just give a little background to this. So when I think, at least when I first started hearing about this idea of poleward expansion of circulation with climate change, it was really this Scheff 2005 GRL paper that's now kind of classic. And he wasn't strictly speaking of the Hadley cells, but he was still speaking of poleward shifts in the storm tracks and sort of the extratropical general circulation. And he pointed out that if you look at the structure of precipitations from the North Pole, through the subtropics, the equator to the South Pole, if you'll see that in the CMIP, this at the time was the CMIP 3 projections. It works well for the CMIP 5 projections. The zonal mean responsive precipitation to global warming is positive north of, poleward. Let me get the arrow here. So this black dot is the maximum of precipitation in the climatology in the CMIP 3 models. And so poleward of the existing maximum, you have increases in precipitation. Then equatorward of the existing mid-latitude precipitation maximum, you have reductions as the sort of the subtropical Hadley-related dryness supposedly expands into the mid-latitudes. You see the same thing in the other hemisphere and the same thing in the other season, right? Wetting poleward of the existing mid-latitude precipitation max, but then drying or precipitation reduction equatorward of the existing mid-latitude precipitation max, right? It's sort of this subtropical dryness replaces mid-latitude wetness, as we've been hearing about. So this zonal mean perspective is what gave rise to a lot of these concerns that a lot of subtropical land could see reductions in precipitation with major consequences. And then this was highlighted again a few years later, now more than 10 years ago, but I feel like this sort of framed the way a lot of the field thought about this. So Jen Lew et al. Had this paper where they showed that each dot here is a different model. The x-axis was how far poleward the Hadley cell edge moved in that model under a strong global warming scenario. And then the y-axis was how far poleward the zero of the P-E field in the zonal mean shifted poleward. So we're talking about 1 to 2 degree shifts in the latitude at which P-E went from its subtropical negative values to its mid-latitude positive values. which were correlated with the Hadley cell shift. So again, there was this idea that if you looked at the zonal mean perspective, Hadley cell expansion or storm track shift, however you want to think of it, should be drying the subtropics in the sense of precipitation or precipitation minus evaporation. But what I've been thinking about more recently, and of course a lot of my colleagues have been thinking about as well, is that this zonal, I mean, you can compute the zonal mean, but nobody lives in the zonal mean, right? People live in specific places and they live on land. In particular, these subtropical dry zones, right, these regions of strong Hadley descent, that expand poleward with climate change, they're really most pronounced over the ocean. If you sort of look at a map of precipitation or a map of sea level pressure, you'll see this, that they're not so much pronounced where people live. And then on top of that, Jay Hood and Brian Soden have come out with this really nice work recently showing that actually the reason that the subtropical dry zones, at least in model world, expand over the ocean is completely different from the reason they expand over land. In particular, the reason that you see this expansion over ocean that you see in things like maps from the IPCC is because the direct effects of CO2 on the circulation, right, so not mediated by warming, which is the straight up effects of the CO2 radiative changes on the circulation itself, is actually to dry only the subtropical oceans and then actually wet the subtropical land. And then the warming also dries the subtropical land to some degree. So there's this complicated response on land, whereas an ocean is just a strong drying signal coming from the direct effect of CO2. So for more, read Jay Hood's paper. This is very nice. It's nature of climate change. So this is one reason to think that land or regions on land may not be the same story as the zonal mean. The other one is this nice empirical paper that just came from Kevin, from his student Dan Schmidt, showing that if you look at year-to-year variability and you correlate from year-to-year the zonal mean Hadley cell edge latitude with local precip all over the world, you only get relationships, negative relationships, which are these brown colors in certain places on land. So here on the left, they've correlated the northern Hadley cell edge latitude with precipitation everywhere in the world in observations. This must have been maybe a GPC P product or something like that. And they find that if you look on land, it's really only negative correlations in certain spots in the subtropics, right? Central Asia, maybe a little Japan, a little bit of the Western US, a little bit of Western Europe here, and that's it. So I'll do the Southern Hemisphere. And if you correlate with the Southern Hemisphere Hadley cell edge, again, in year-to-year variability in the observations, you really don't see relationships in South America. So the rest of the Southern subtropics, you don't see anything. And similarly, the rest of the Northern subtropics, you don't see anything. So I've circled these regions here, and then I think Kevin and Dan's point here is apart from these circled regions, you really don't see a lot of relationship between the Hadley cell edge latitude and precip or P minus C. So that this idea that the impacts may be more localized than we think about when we read a paper like those classic Yin and Liu papers who are looking at zonal mean diagnostics. Or even when we read a more modern paper like some of my earlier papers that didn't distinguish between land and ocean, this sometimes doesn't come across. So I apologize for that. So then what I wanted to do after getting this letter from Kevin about maybe contributing to the CIRES variations issue is to try to actually look back at some of my old work that didn't distinguish between land and ocean and didn't look so much regionally, really try to see, is there much of a land signal in the CMIP5 projections for precipitation change? And so it's this story about projected subtropical drying. How robust is this on land as opposed to just on Earth? And do we see the same regionality? So, so I'm just going to go over my plots from that 2012 JRLO paper that looked at this question in general, really focus on land this time. And so I'm going to show you a bunch of maps of precipitation in the models and precipitation change in the models. So in every map I'm going to show you, they're for different seasons, has this tricolor scheme where the red colors mean almost all the models have precip reductions in the 21st century. Blue colors mean almost every model has precipitation increases in the 21st century, and the white colors mean, or light colors mean the models don't, almost all the models don't change precip much over the 21st century. So, and then we're really going to focus on these red colors where the models consistently project drying, and then try to understand, does that seem to go with this tropical expansion story? Where does it? So watch out for the bold red colors on these plots, and then all the plots for reference are going to have black contours on them that show the climatology of the precip in the models. And the light contours meaning lower amounts of precip, and the bold colors meaning much higher amounts of precip. Right, so I'm just going to show you 4 maps like this and sort of carefully analyze to what extent they're consistent with the subtropical expansion leading to mid-latitude drying story that we've heard about. So here's what this looks like in December through February. So again, black contours are the climatological precip according to the models, and their colors just show where the models agree versus disagree on precipitation reductions versus increases. So you can see that there are a lot of very striking precipitation reductions projected in this season in DJF with climate change. But a lot of them are, they are associated with the poleward edges of the subtropical dry zones, right? So here's like a subtropical dry zone over the Indian Ocean. Here's a mid-latitude storm track. So here's that poleward edge that was just highlighted by Nick in that nice little diagram. And so you can see that there is a lot of drying here, just as you'd expect, but you can see almost all of it's over the ocean because this is just too far poleward to affect Australia in this particular season. This is Australia's summer. And so if you look globally, you see that actually these dark red regions of robustly projected precipitation decline really only intersect land at a few places. So the Mediterranean is probably the most famous one, right? So a lot of the Mediterranean, Middle East really does look like it's projected to dry under global warming due to poleward expansion of the Sahara. So that story looks pretty good. And you see it also here in southern Chile. It's another place you hear a lot about. Looks like you may see here something in Mexico, but this doesn't seem to be associated with poleward expansion of any dry zone, right? We're not seeing this. This red is not located sort of maybe up here at the poleward edge of the subtropical dry zone, or even here, right? It's sort of located in a relatively wet zone. And it's actually, this is a spurious wet zone. Mexico has actually almost no precipitation in winter. And actually, David Battisti has some interesting work on why the models might be simulating the spurious maximum, but I'll just leave it at that. So in DJF, it's really just these regions I've circled in yellow to the story that we hear actually really seems to apply to in the CMIP 5 projections. So just the Mediterranean, Chile, because everything else is either over the ocean or it's spurious, or in the areas that are on land, you just don't see the red colors. You just don't see a strong signal, for example, here in subtropical Australia or here in subtropical Asia, right? It's just the models are muddled. You get these lighter shades implying not as robust a response. And so if you go to March, April, May, you see something similar. So again, there's a lot of dark red, but a lot of it's over the ocean. And where it intersects land, it's just, again, it's a few more places than in DGF, but it's not much. So the Mediterranean shows up again. A little bit of the western U.S. shows up now, right on the poleward edge of the subtropical dry zone in the western U.S. So this looks like sort of classic poleward expansion here, sort of the southwest United States. Chile again, and then you start to see, I guess I covered it up here with the circle, you start to see just a little bit in the Cape region of South Africa as they're starting to get into their autumn, into their rainy season. But again, that's about it, right? The rest of subtropical land, you don't see any dark red on this map, right? It's just in those circled regions. So in June through August, you start to see a little bit more, especially in the northern hemisphere. Not much going on in North America anymore, right? North America is pretty much all muddled, right? Non-robust or weak responses. But Europe is now kind of on this edge between the subtropical dryness and mid-latitude wetness. So Europe, all right, sees this robust drying, and then you sort of see Chile. You start to see the very southwestern tips of Australia and Africa drying as well. But then a lot of these other red colors on land don't seem to be associated with subtropical expansion. For example, in South America, this is happening in the deep tropics, right? So this signal here would not be associated with poleward expansion of the subtropical dry zones. Similarly, these red colors in interior southern Africa here look very dire, but this is a place, again, like Mexico, that receives almost no winter precipitation in the first place. And so this is kind of inconsequential. In this area, almost their entire precipitation is coming from seasons other than JJA, so that's why I haven't circled it. So the yellow circles here are where this may be relevant in JJA, and then I'll maybe just go quickly in the interest of time here. In the fall, there's a few more interesting spots. So you see this very strong signal now in interior southern Africa, and it does maybe seem to be associated with real precipitation right now, so this could be important. And then maybe some South America stuff that maybe looks a little bit more like poleward expansion of this dry zone now, and a lot of the same usual suspects besides. You can read more about it in my contribution variations. But in every case, right, in every season, there's huge areas of subtropical land, including areas on the transition between subtropical dryness and mid-latitude wetness that Nick introduced at the beginning of his talk, that we all talk about in the introductions to our papers, in which we don't see any model signal towards drying. So for California, I know Isla has some nice dynamical work explaining why this may be, and why models might be actually missing it a bit in California. But if you look, at least in a lot of places, the models don't seem to be projecting this everywhere, except only in certain parts of the subtropics. So just to sum up, what I like to think about this is that clear drying projections for the future in the models due to subtropical expansion over land are actually pretty confined in space. They're robust where they are, right? But they're only in certain places. And most of the red ink on those plots, most of the robust subtropical expansion drying is actually over the ocean. And that makes sense because the ocean's where the dry zones really live, right? So look at all these different subtropical dry zones outlined in the light contours. They're mostly ocean-centric except for this Saharan one here. So it kind of makes sense that that would be the case. But then this doesn't really explain all of it because even if, looking over both land and ocean, there's plenty of these transitions from subtropical dry to mid-latitude wet that you don't see any red ink at all, right? So that just because the zonal mean sees this replacement, this sort of expansion of subtropical dryness doesn't mean that you see it in every longitude or every part of the world, but only in some. And that's regardless of land and ocean. I also didn't point out that part of why we don't see a lot of it on land is that in some parts of land, there isn't, you don't really see a transition from subtropical dry to mid-latitude wet anyway, right? So in the eastern North America, especially, the subtropics are quite wet, and then precipitation declines as you go forward. So expansion of the subtropics couldn't possibly dry this part of the world, for example, at least in this particular season, because there's no subtropical dry zone to expand poleward in the first place. You just sort of have this broad, moist southwesterly flow that comes up from the Caribbean, and this whole part of the continent is wet. So I skipped that during showing the figures, but I think this is also part of what's going on as well. So again, I speculate more about this in the variations article, and that's all I have. Thank you.
Great. Thank you very much, Jack. I think that was a nice concluding presentation to tie all this together with the impacts. Sure. Any questions for Jack or any three of our other presenters? We can take those now here, so I'll pause for a minute. Looks like we do have a question here. It came in through the chat, so I'm going to read it out loud. Nick, this question is for you, so if you could take yourself off mute, that would be great. The question comes from Zhao Wang. She asks, can the same global metrics be used to evaluate the width of the tropical belt over individual basins? What should we be cautious about when applying the same methodology to regional Hadley circulation?
Yeah, that's a good question. So, one difficulty is if you try to take something like the stream function to individual basins, it's probably not advisable because you can't really close the circulation from a mass budget perspective unless you're really careful. So I'm not sure it's very easy to look at something like the overturning circulation basin by basin with metrics, because as soon as you do that, you need to think about the Walker circulation component, but also other regional circulations. And so I think too with what's Jack shown with the sort of precip projections, this is very zonally asymmetric. There's a lot of fine scale detail. So I think at least I would guess that if you're interested in looking at regional projections of these things, it's fairly safe to stay away from some of the metrics themselves. Maybe looking at oceanic centers of action like the subtropical highs, because that's where the air is actually sinking, is more advisable. None of these metrics that I've discussed are probably that amenable outside of the zonal mean, except something like the tropopause break, and unfortunately that doesn't really relate to the Hadley cell edge. So I would say it's an open topic still on what metrics we can use outside of the zonal mean, but I think at that point you also need to start considering the zonal asymmetries as you get more granular.
And Jack, did you want to ask a follow-up regarding some of the metrics?
Oh, no, it's just a quick comment on that. That I don't know if I'd be as pessimistic as Nick, in that I think that in almost every longitude you're going to have a wind reversal from easterly trades in the tropics to mid-latitude westerlies in the mid-latitudes, and so maybe you could still use that surface U equals 0 latitude. Though maybe that's not going to work in the monsoon regions, but perhaps in a lot of the rest of the world, I think that would work. I haven't thought a lot about this, though. That was one of your metrics, Nick, wasn't it?
Yeah, I guess that could be interesting, and you wouldn't really expect to have to worry about latitudes where, it reverses multiple times. I think it is pretty robust. I mean, yeah, I guess that one you could probably look in individual basins more
Yeah,
effectively.
I was just speculating, but I thought maybe that one might be relatively clean because there are these broad reasons why you have a lot of easterlies in some latitudes and westerlies in other latitudes, and that, except for the monsoons, that shouldn't depend too much. I don't know. It was just a guess.
Yeah. No, that's a good point. It's something where you don't want to say no outright because no one's really deeply looked at it. So I guess that's
right.
Maybe I should revise it and say we don't really necessarily know how well they work, but in principle, something like U=0 could probably work.
Yeah, I guess I was thinking of some papers where the Australians have. I guess they didn't use they actually used the SLP max. So the Australians used their local SLP subtropical ridge to quantify this, and I think they got some reasonable definitions out of that. But I don't remember which paper that was.
And I want to add a comment that Zhao also made. She's saying that we can define the mass stream function using the irrotational component of the V-wind, which separates the Hadley and Walker circulations.
Yeah, I guess I'm still, I think U=0. It's hard, right? Because if you zonally average across, say, a basin to look at something like I don't even know if I'm comfortable. This is a big debate right now with this sort of regional. Can you call something a regional Hadley circulation? I mean, is that a sort of misnomer because the Hadley cells and the Hadley circulation are sort of the little mean construct first? And I'm not sure how the metrics would work, but in principle, I mean, you can look at the overturning definitely in something like the Pacific Basin alone, and get. I mean, ultimately, that's what you have to do if you want to understand the physics here. I mean, you can't live in the zonal mean forever. So, I mean, I would agree you need to push to understand these things more basin by basin, but I'm just. There's no easy answer right now for how do the metrics work and relate outside of the zonal mean. It is still really active area of research.
Great. Do we have any other questions? We do hear from Amy. Let me take you off mute. Amy, please go ahead.
Hi. My question is for Isla. Hi, Isla. I'm wondering, is there an explanation for why the reanalysis gives such different trends? Is that sort of just expected, or that from the assimilated observation differences or the model differences?
Yeah, so well, Kevin has done quite a lot of work in a paper that should be submitted soon looking at all the different reanalyses, and he's shown that the older ones, when you look at the stream function metric, the older ones seem to agree less with the modern ones, and you can imagine that they're not being so well constrained in the divergent circulation. For the ones I was showing, so that you would expect that ERA interim, MERA 2, and JRA 55, they're all modern reanalyses, but they're and I had it on my slides before, but I didn't really want to go into the details. There's a paper by DeWeaver and Nigham, I think in the 90s, that talks about the ability of the incremental analysis update procedure that's used in the MERA reanalysis to constrain the divergent circulation. And whether this is relevant to the present MERA reanalysis, I mean, it was a much older version of the NASA reanalysis that they were looking at. Whether it's still relevant, I don't know. But they showed for particular ENSO events where they had some other observations that the ECMWF reanalysis worked much better at constraining the divergent circulation than the incremental analysis update procedure that's used for the product I showed there for MERA, which is done a bit differently. So I think based on that one paper that there could be reasons to suspect that MERA is less good at constraining the divergent circulation. And so for that reason, I would suspect that we should trust ERA interim and JRA 55 more. But that's pretty speculative.
Thanks. Do you know if the trend depends at all on exactly which endpoint you use? Because it looked like in particular 2016 was quite different, but a lot of the rest of the years were closer.
I'm not sure. I don't know if I can go back to the slide.
You can, yeah.
I can.
Yeah, go ahead and pull that up if you want. I'm not sure which slide it's on, so you would know best.
I suspect it's probably pretty robust to that, because I don't think it's just the endpoint that. I guess it's there on my title slide.
Which slide was it, Isla?
There we go.
There you go.
Yeah. Maybe that's making quite a bit of difference. But I do know that I think Chaim Garfinkel, he had a paper in 2015, so before 2016 had happened, and he actually showed that there is also a difference between the two. So MERA produces two products. One is the one that's kind of just done in the same way as other reanalyses, and the other is the one that comes from the model after imposing the incremental analysis updates. And he showed that those were also different between those two products, and I used the latter one. So it's a good point. I should probably check the degree to which that matters. Maybe Kevin has a better idea, because I think he's looked at this a bit more. But I still suspect that MERA will be different from the other reanalyses, even without 20.
Kevin?
Yeah, so I just comment. So that of these, so I've also looked at the CFSR reanalysis, which is sort of another more modern reanalysis, and it agrees very well, with this surface wind metric that Isla is looking at, with the ERA interim and JRA 55. They all almost give exactly the same trends over this 1979 to 2016 period. So it's really the MERA 2 that seems to be the outlier among the sort of more modern reanalyses. And in terms of the endpoint, there's certainly some fluctuations from year to year, but I think in general the sensitivity is actually not all that severe to the endpoint, with some exceptions maybe in the northern hemisphere edge. But in general, I think you get a qualitatively similar trends using an endpoint from, say, 2005 all the way to 2016. So.
Thank you.
Great. Thanks, everyone. If there's no final questions, I think we can go ahead and wrap up for today. Thank you again to all of our speakers, both for contributing articles as well as taking the time to present today. And thanks, everyone, for tuning in. I hope you have a great rest of your day. Talk to you soon.